The modern global economy moves tens of millions of tons of cargo every single day. Look at commercial aviation alone. Machines weighing hundreds of thousands of pounds hurtling through the sky, carrying everything from microchips to medical supplies. To get back to the ground, those massive machines have to slam into a concrete runway at over 150 miles per hour. In a fraction of a second, a free spinning wheel must accelerate from a complete standstill to matching the immense velocity of the aircraft. That violent transition generates an extreme amount of friction. All that friction converts directly into heat. Within half a second of touchdown, the surface temperature of an aircraft tire spikes to around 260 degrees Celsius, or roughly 500 degrees Fahrenheit. Every commercial flight, every heavy cargo plane, and every piece of heavy machinery relies on specific materials that can absorb this repeated kinetic violence and heat without blowing apart thousands of times a day. The obvious engineering solution is to manufacture a custom synthetic rubber in a lab. For standard car tires, we actually do use synthetic polymers, like butadiene rubber. But heavy industry requires something far more resilient. If you put a pure synthetic tire on an airliner, it would fail instantly. Synthetic rubber physically decomposes and melts into smoke at just 151 degrees Celsius, falling hundreds of degrees short of what an aircraft needs to safely land. There is exactly one material on Earth capable of surviving these parameters. It's called cis-1,4-polyisoprene, or natural rubber. We don't synthesize it. We have to literally score the trunk of a Hevea brasiliensis tree and watch the white latex strip out. At the molecular level, natural rubber operates like a biological nanocomposite. When the material is subjected to the immense stress of a landing, its chaotic, tangled polymer chains instantly snap into a highly organized semi-crystalline grid. This is called stress crystallization, and these rigid regions actively stop microcracks from tearing it apart. This chart shows the tensile strength of a natural rubber tire plotted against temperature. While the material weakens as it heats up, you can see it maintains enough of its structural integrity right up into that 500-degree landing threshold, allowing the tire to stay intact. We manufacture titanium airframes and program complex flight computers, yet our heaviest aerospace engineering remains entirely tethered to the unsynthesizable biology of a single species of tree. Today, over 90% of the world's natural rubber is produced in Southeast Asia. Geographically, that is a paradox, because the rubber tree is exclusively native to the Amazon basin in South America. The entire Asian industry traces its origin to a single event in 1876. An explorer named Henry Wickham smuggled 70,000 rubber seeds out of Brazil and shipped them to the botanical gardens in London, permanently shifting the global supply chain. But only 4% of Wickham's stolen seeds actually germinated. In the end, just 22 trees were successfully transported and planted in Singapore to serve as the foundation for an entirely new agricultural empire. Because those 22 trees were repeatedly bred and propagated, the millions of acres of rubber plantations currently covering Asia are all descended from that initial tiny batch. They are known as the Wickham clones, and they share a functionally identical genetic makeup. For over a century, growers aggressively selected for one specific trait: maximum latex yield. In the process, they inadvertently stripped these clones of their natural biological defenses, creating a highly vulnerable target. This undefended monoculture faces a very specific, lethal threat. It's an obligate fungal pathogen called Microcyclus olae, and it causes a disease known as South American leaf blight. The fungus aggressively targets the tree's youngest, most immature leaves. It colonizes the tissue, breaking out in powdery gray-green spores that cause the leaf to warp, shrivel, and drop prematurely. Stripped of its foliage, the tree expends its remaining metabolic energy trying to push out a new canopy. The fungus immediately infects that new growth, triggering a continuous cycle of defoliation that drains the tree until the branches dry out and the entire organism dies. This exact pathogen is the reason large-scale commercial rubber plantations no longer exist in South America. The blight already swept through the continent's commercial farms and decimated the industry there. The Asian rubber empire, which currently supplies the entire global economy, only continues to function because an ocean currently separates the vulnerable clones from the deadly fungus. urgent barrier is failing due to the speed of modern globalization. Direct flights, transcontinental cargo shipping, and shifting climate zones mean the transfer of living fungal spores from South America to Asia is a high probability event. If a single viable spore breaches the Wickham clones, the outcome is mathematically predictable. Lacking the genetics to fight it, the disease would spread entirely unchecked through the dense, uniform plantations, rapidly choking off latex yields and killing the trees. As the supply of natural rubber evaporates, the production of heavy-duty aviation and industrial tires simply stops. Without replacement tires, commercial airliners and cargo planes would be permanently grounded on the tarmac. The failure cascades outward across the entire logistical network. Long-haul trucks lose their treads. Cargo ships rot in ports without the inland transport needed to move the goods. The physical movement of the global economy grinds to a halt. We operate artificial intelligence, quantum computers, and orbital rockets, yet without a highly specific, unsynthesizable molecule extracted from the sap of a single, highly vulnerable plant, our global civilization stops moving. We are one microscopic fungus away from returning to the 19th century.